of the eigenvalue of the Hermitian matrix, right? So what is a Hermitian matrix? It's a type of matrix. What is the definition? Okay, great. Hermitian conjugate. Okay, I did not mention this word, you know that. So it's like taking the transpose and then the complex conjugate, right? So it's a Hermitian conjugate and then it's equal to itself. Okay? So it has real eigenvalue. So let's prove it, right? I probably won't ask you to prove anything in the exam, right? Because nowadays it's not that important. ChatGPT can do it for you. But you should understand the flow. And the process of doing the proof is to train your brain and also make clear some of the concepts, right? For example, when I say I let the eigenvalue of A, you know, is a matrix. It has eigenvalue lambda I and eigenvector lambda I. And I hope now you won't get confused that, oh, this is lambda I, this is lambda I, are they the same? Something like that, right? You should understand this is just a number, a scalar, and this is a vector, and the lambda I inside is just a label. Again, a label can be anything. And you know that this vector means that it has the corresponding eigenvalue lambda I. That's it, right? And then what it means? It means A times this vector. We really can just call this vector equals lambda I times this vector, right? That is the meaning of eigenvalue and eigenket or eigenvector. Okay? So I hope that now you're very familiar, confident with the bracket notation. So I'm going to prove it. Last time I stopped here. I say, okay, I'm proving. Now I start with this sandwich. Bra, matrix, cat. So you should know, right? What is it for the whole thing? Is this a number, vector, or a matrix for this whole thing? Number. For those who forgot, just think about the matrix form. Lambda cat is a what type of vector? Column vector, right? And A is a matrix, so it's a square. And then a matrix times a vector, you get vector, right? And then vector, inner product with the bra. Remember, bra times cat is inner product, right? It must be scalar. I'm sure many of you still feel confused. Same for me when I first studied this, right? So you need to keep asking yourself until a point you are not worried about that. When we are not worried about that, then you can spend your efforts in understanding the proof, right? So this process, I want you to continue to think about this. Okay, now then let's continue. So this one, right, the proof is given to you. I claim that this is equal to lambda I, lambda I, lambda I. Very confusing again, right? But you think of it carefully. Why can I say that this equal to this? Because I apply A to cat, then what does it mean? When lambda I vector is its eigenvector. Look at this. What I have done is just that, use this equation. A applied to the eigenvector equals to eigenvalue times eigenvector. So what is this lambda I here? Is this a number, cat, or vector, or a matrix? Just a number, right? Although I put in the same location, I really don't need to make a bold face for you or put something on double bar on top to tell you this is a matrix, right? This is just a number. What happens if you have a number times a number? So number times a vector, and then bra. I can factorize out the number. Is this okay? If you don't agree, think about the matrix form. What I'm trying to say is like this. AB times E times AB. Is this just equal to AE times AB times AB? Am I right? That's all I'm doing. Of course, we do this because we base on the linear space theory. We know that I did not talk about this basic rule, but you are allowed to take out the number. Any question for this, right? It's not about the proof, it's about do you feel comfortable with these three knives? You need to be very comfortable. If you have doubt, you should ask. Make sense? Distribution here, actually not exactly distributive. It's just a number. A vector times a number times a vector. I can take the number to outside, right? So what do you call? It's not even associative. A property of linear system, yeah, or commutative. You can commute these two in that sense, yeah. But it's a property of linear system. That's right. Is this clear? If no, you should ask, right? Because we'll be very fast later. Now, I want to make a simple assumption, okay? I assume we don't need to, but I just want to go over these slides quick, okay? So let me assume, because this is what we are doing in quantum computing. Lambda I is normalized. Okay, I assume it is normalized. I don't have to, but just assume normalized, okay? Then what does it mean? This becomes what? Lambda I, why? Very good. So inner product equals to 1. Okay, he did study or he learned from another class, right? Lambda I. Okay, so that's the first thing. Okay, that's the first step. So, okay, now consider, now we try to do it. Now consider 2. I do the same thing, but you told me this is a number, right? So I can apply a complex conjugate to it. Any number has its complex conjugate. I consider the complex conjugate of this number. Now, it's very messy because I did not write it well, right? But you should not have problem or feel confused when you see this because now you're very familiar with the system. This is bra lambda I times A times cat lambda I. Okay? Do not think that, some a bracket lambda I with 1A, 1 lambda I, another bracket. No, right? This is not for quantum computing. Okay? Okay, so let's continue. What is this? Do you remember the equation where I apply a complex number to it? We learned it last time. You probably forgot. Let me remind you. It is this. If you have two vector A times a matrix N, B, right? Like this, star is equal to B, M dagger A. Okay, you just swap them. Okay, we proved that already. Again, forgot that is fine. Put in your cheat sheet. You need to memorize it. Really, memorize is good. Okay, so what is this? If I apply this star to it, can someone tell me? Can you go from left? Cat, what type of bra? It's the same. Very good. You still swap them, but it's the same, right? Still lambda I. And then A dagger, and then lambda I. Okay. Now, but this one I claim that equals to lambda I, A, lambda I. Do you agree? Why? Thank you. Because A equal to A dagger. That is our assumption. We say this is a Hermitian matrix, right? Then we repeat the same thing as the previous 9. This equals to lambda I. Okay? Then what does it mean? Then I continue. Therefore, Therefore, it say that maybe I do one more step, will be better. Okay, then from here I continue from number 2. What do I get? I apply the star to both sides. A lambda. Sorry, my writing is getting worse. Lambda I, A, lambda I star equals to lambda I, right? This is what we prove from 2. I just say that this one equal to lambda I, so this equal to lambda I, right? What if I apply one more star to both sides? Complex conjugate is just itself, right? So it means lambda I A lambda I equals to lambda I star. Do you agree? Let me call it free. From 2, right, we get 3. So what do you see? Then from 1 and 3, we see that lambda I A, lambda I equals to lambda I. Lambda I A, lambda I equals to lambda I star, right? Then what does it mean? It means lambda I equals to lambda I star. What type of number equals to is complex conjugate? Yeah. Must be real, right? So lambda I is real. Okay, and we prove this one. Now this is a little bit messy actually. If I ask you to prove in exam, same for me, I might just go into the wrong loop. You keep looping, cannot prove it. So you just understand it will be good. But the point is, you really need to go back to really train yourself to be comfortable with all this writing, right? You ask ChatGPT to give you something similar, you need to understand. Okay, so we prove that the eigenvalue of any self-adjoint or Hermitian matrix must be real. That is a very important conclusion. And also, Hermitian matrix is very important in quantum computing, in quantum mechanics. Okay, this is your friend now. We need to know everything about it. Okay, any questions? Thank you. Okay, if not,